Hello. Having now looked again at Newtonian physics, we are now finally in a place where we can look at how classical thermodynamics works. As I explained in my videos on Newton's first law, we can introduce classical thermodynamics by considering an analogy with Newton's laws, as the mathematics undermining both these theories, essentially calculus, is exactly the same. With that in mind, let's begin by briefly reviewing what we have learned. We have learnt that physical theories all try to answer this ancient question on the nature of change. Furthermore, because we want to quantify how much things within the system, a part of the universe, will change in response to different external stimuli, we state that change happens when something external to a system acts upon it. The first step in developing physical theories is thus to determine how the system behaves if no external stimulus acts upon it. Let's now try to do this by thinking about how the state of this lump of material could be characterized. Let's do this by trying to work out how this piece of material will behave without any external stimuli acting upon it, by thinking about the sort of things that external stimuli would do to the system and ruling these out. A first external stimulus we could apply would be a force. We could essentially pull on the material and stretch it out. This would change the volume of our lump of material. We could thus conclude that volume only changes if an external stimulus acts upon the material. A second thing we could do to this system is that we could heat it up. This would change the temperature of the material. We could thus conclude that in the absence of an external stimulus, the temperature of the lump of material will be fixed, and that the temperature of our lump of material, the system, will be the same as that in the surroundings, the environment. Let's last of all place our lump of material in contact with a second lump of material. In the absence of any external stimulus, the number of atoms in the blue lump of material will stay fixed, and the number of atoms in the green lump of material will stay fixed. These quantities that we are discussing here, volume, temperature, number of atoms, and so on, are known as thermodynamic variables. We use thermodynamic variables to define the state of the system, and we divide the set of all thermodynamic variables into two broad classes. Extensive thermodynamic variables are quantities such as number of atoms and volume that depend on the number of atoms in the system. Intensive thermodynamic variables, such as temperature and pressure, meanwhile, do not depend on the number of atoms in the system. Please learn the meaning of these two words, intensive and extensive, as soon as possible, as this distinction really is essential to everything that we will do in this course. Now that we understand what a thermodynamic variable is, we are in a position to state the law of thermodynamics that is equivalent to Newton's first law. Remember, as always, that we are trying to develop a physical theory that explains the nature of change, and that we have defined change as the thing that happens to the system, a part of the universe, when an external agent acts upon it. In Newtonian physics, we had the following statement of the first law, which contained that all-important word external, and that then had a statement explaining how the system behaves when that external agent is not actively involved in the system's business. With this law in mind, let's give a statement of this sadly unnamed law of thermodynamics, which is the thermodynamic equivalent of Newton's first law. This law states that any physical system remains in equilibrium with the values of all extensive thermodynamic variables fixed, unless acted upon by an external agent. Notice that once again we have this word external here, and that this statement, the statement of the law, answers the question, how does the system behave when it is not being acted upon by anything external to it? The answer, it remains in equilibrium with the values for all extensive thermodynamic variables fixed. Let's now consider what the external agent in thermodynamics can do to the system. Remember, in Newtonian physics, the state of the system, the manner in which the system behaves if it is not acted upon by an external agent, is characterized by the momentum of the system. The external agent must therefore change the momentum of the system. It does so by applying a force, essentially a push or a pull, to the system. The problem for classical thermodynamics is that the state of the system is characterized by many extensive variables. We can thus change the state by doing a variety of different things. For example, we can change the state of this system here by pulling on it and thereby changing its volume, or by lighting a fire underneath it and thereby changing its temperature. We thus need a way of quantifying the degree to which each of these external perturbations will change the state of the system. We can no longer simply state that the system changes when a force is applied to it. It is very useful at this point to introduce the notion of a thermodynamic phase. A phase is basically a part of space. I can thus divide the system shown here as a blue box into two subphases, phase 1 and phase 2 as shown here. In doing so, I have divided the total number of atoms and the total volume of the blue box between the green and purple boxes as shown. To each of these phases, I could then ascribe a value for the various extensive variables. So, for the purple box, phase 1, has a number of atoms n1 and a volume v1. The green box, phase 2, meanwhile, has n2 atoms within it and a volume v2. Obviously, the total number of atoms in the system is equal to n1 plus n2, and the total volume of the system is v1 plus v2. In addition to ascribing values to the extensive variables in each phase, I can also ascribe values to the intensive variables in each phase. I can thus say that the purple box, phase 1, has a pressure P1, while the green box has a pressure P2. Having defined this notion of a phase, we are now in a position where we can give a statement of the zeroth law of thermodynamics, which is the law in thermodynamics that serves the purpose Newton's second law serves in physics. Furthermore, eventually we will use this to quantify how much the system will change when an external agent acts upon it. In classical thermodynamics, our external agent is going to be a second phase, and we are thus going to write that the extensive thermodynamic variables that characterize the state of any given phase will change if that phase is placed in contact with a second phase which has different values for the intensive thermodynamic variables. Let's consider the meaning of this statement by examining how the two-phase system shown here behaves. Let's suppose that P1 is greater than P2. We know that phase 1, the one on the left, will expand as a result of this pressure difference, and its volume will thus increase. At the same time, the volume of phase 2 will decrease, because I am requiring here that the total volume V1 plus V2 remains constant. As the volume of the first phase increases, the pressure within it will decrease, so P1 will decrease. At the same time, because the volume of the second phase decreases, the pressure goes up, and the expansion of phase 1 stops once the pressures in the two phases are equal. We thus state that at equilibrium, the intensive thermodynamic variables take one single uniform value across the whole system. Now that we have introduced all these things, we are finally in a position to see how we can construct the physical theory of thermodynamics by analogy with Newtonian physics. In my previous videos, we have seen that constructing a physical theory is a three-step process. We first define how the system, a part of the universe, behaves when it is not acted upon by an external agent. We then quantify how the system responds when an external agent acts upon it. And then last but not least, we define some conservation principles. In Newtonian physics, these three tasks are done by the three laws. The body remains at rest or travelling at a constant speed unless acted upon by an external force. The force acting upon the system and applied by the external agent will cause the momentum of the system to change. Then, last but not least, We have the conservation principle enshrined in the third law that tells us that if the momentum of the system increases, the momentum of something in the environment must decrease by an equal amount. In other words, every action, and remember action is not force, has an equal and opposite reaction. In classical thermodynamics, we cover these three bases as follows. We state that a physical system will remain in equilibrium unless an external agent acts upon it. When the system is at equilibrium, its state is characterized by the values of the extensive thermodynamic variables. We then introduce the notion of a phase in order to describe how the system couples to its surroundings. We state that if two phases with different values for one of the intensive thermodynamic variables are placed in contact, then the values of the conjugate extensive thermodynamic variables in the two phases will change. So for example, if two phases with different pressures are placed in contact, the volume of the lower pressure phase will decrease while the volume of the higher pressure phase will increase. This process will continue until the pressures in the two phases are equal. Our conservation principle then asserts that the total values of these extensive variables in an isolated system composed of various subphases cannot ever change. For our purposes here, an isolated system is one that cannot exchange anything with parts of the universe that are external to it. The whole system can thus not expand or contract, and the total number of atoms within it must be fixed. What this means is that if two subphases within our system come to equilibrium, then any increase in the value of the extensive variable in one phase must be counterbalanced by a decrease in that value for the second phase. This all maybe seems rather straightforward, and it is straightforward when you think of it in terms of volumes and numbers of atoms. What makes thermodynamics difficult and confusing is that we have to consider heat transfer and temperature. And during the next few videos, we will spend a lot of time doing that. But we will see that the mathematics is the same as the mathematics that we've used throughout these videos. Thank you for your attention.